Hello students, welcome you all to the next session regarding discussion of module number 3, that is steam turbines. In the previous sessions, you have learned regarding the analysis of different kinds of turbo machines to draw the velocity triangles for different kinds of turbo machines with different conditions. Then to estimate and calculate the various parameters such as the energy transfer, power developed, then the utilization factor, degree of reaction, and many other things also. In today's session, we'll be starting with next module, that is module number 3, the steam turbines, where we'll be discussing introduction to steam turbines, classification of steam turbines, then the working procedure of the impulse kind of a steam turbine with a derivation where we'll be deriving the maximum blade efficiency and some of the terms which will be related to the steam turbines for the impulse type. So already, as I said for the previous video lectures also, if you have any kinds of doubts, you can send me an email to this email IDs, which I have already highlighted on the screen, which you can see here. These are my following email IDs. And even you can send me an WhatsApp to the mobile number, which is displayed on in your screen. So with these things, we shall now begin the today's session. So the first introduction part. Basically, the steam turbines which you have learned or which you have heard, they are nothing but their steam turbines are the devices, or you also call them these devices as the prime movers. These are the prime movers, especially they are used in the steam power plants where the electricity is generated by, or the power generated by, utilizing the kinetic energy of the steam which is coming from the boilers. So in the boilers, when the steam is being generated, it is then passed to the turbine blades, where by the rotation of the turbine blades, the power is generated. So therefore, the incoming kinetic energy of the steam, it plays a very important role. So therefore, the incoming kinetic energy of the steam, it is having a high pressure and high temperature, which is responsible to convert this into a high velocity or jet of a steam. And this is done when it passes through a device, we call it as nozzle. So here nozzle is a device which is responsible for again increasing the kinetic energy of the incoming steam from the boiler, such that with a higher kinetic energy, when it strikes the turbine blades, that is the curved blades, it causes them to rotate on a rotating shaft. As a result, the shaft rotates and the energy is generated. Maximum times, the axial flow steam turbines are much preferred when compared to the radial flow turbines because they can generate good amount of power. These are some of the points with respect to the introduction of the steam turbine. The next, classification. So generally the steam turbines we are classifying based upon various kinds of factors. The first one is depending upon the action of steam. If a sudden force is applied, onto the steam, or sorry, if a sudden force is applied onto the blades, then we call that kind of force is the impulse force. But along with the force, if there is a reaction force also is responsible. When a force is applied, if we get another reaction force developed, which is responsible for generation of energy, we call it as a reaction type of a machine. So this reaction, in other words, you can say that it is almost based upon your Newton's third law of motion, where you have learned that for every action, there is an equal and opposite reaction which is being developed. So when action is applied on a body, you know that there is a reaction force which is developed in the same direction of the application of the force itself. So this is, there are some turbines where the reaction force is also used. We call them as the reaction turbines. This is the first point. Then, depending upon the direction of action, steam flow, they are classified into the two types. Already this we have discussed in our module number 2 also. If the steam is flowing along the axis of the rotating shaft, we call them as the axial kind of turbines. If they are flowing away from the, or it is moving away from the axis of the shaft in the form of a radial direction of the blades, we call them as a radial flow. Then we have a number of pressure stages. So In some of the turbines, the steam expansion, already you have learned in a vapor power cycles, the expansion of a steam takes place in only one set of blades. We call those as a single stage turbine. If the expansion takes place in only one stage, we call it as a single stage turbine. Or if the same expansion, if it is taking place in more than one set of turbines or one set of blades, if it takes place in more than one set of blades, we call them as more than one. That is 2, 3, or like this, it goes on continuing. Then we call them as the multi-stage turbines. We call them as a multi-stage turbines. So therefore, multi-stage turbines are those where the expansion of steam takes place in more than one stage, more than one stage. Then moving on to next, method of governing. So I told you method of governing is nothing but it is responsible for increasing the kinetic energy of the incoming steam. It may be done with the help of a throttle, it may be done with the help of a nozzle, or by having a bypass also. Then depending upon the application in industries, sometimes the turbines, depending upon their stationary behavior or non-stationary behavior also, they are preferred. In the stationary, again depending upon we are having two sub classifications, that is the constant speed as well as the variable speed. And the last is the pressure inlet to turbine. So pressure inlet to turbine, it is having different kinds of conditions. The first condition, if you observe here, it may be on the form of an low pressure turbines. If there is a medium pressure in the steam, you can use medium pressure turbines. Then you can have high pressure turbines. Also, if the steam pressure is very much high, then you can go for very high pressure turbines. And if the pressure is so much high that it crosses beyond the critical point, then you can go for even the supercritical pressure also. So therefore, you can say that around 6 types of factors are responsible for classifying any kind of turbine, starting from these conditions which you can see on the screen. The first one is the action of steam. Second one is the direction of steam flow. Third one is regarding the number of pressure stages. And the fourth one is the method of governing. Fifth one, usage in industries. And sixth one is the pressure inlet to the turbine. These are some of the factors. Now moving ahead, generally any steam turbine you take, it is classified into two types. That is the impulse steam turbine and another one is a reaction steam turbine. Out of that, this is the first case, that is the impulse steam turbine. So if you observe the picture on the left side of your screen carefully, this is the first picture. If you observe here, this particular picture, you can see that you can see that there are some of the curved blades. You can see these are the curved blades, and these blades are mounted on a ring. We call this as a rotor. This is a ring rotor, and here at the center we have a shaft on which this rotor is being mounted. So as these blades start to rotate, then the shaft also rotates and the energy is being generated, which you can see here in the bottom figure also. If you observe in the bottom figure, here is that shaft which you are observing here, and this shaft is under rotation. When these blades, you can see, has shown a small sectional view here. When the steam which is coming from the nozzle, if you observe here, when it hits these turbine blades which are curvature nature, they causes these blades to rotate, and in turn the shaft also rotates. So you can see here we are having around 4 nozzles placed at different positions. This is nozzle number 1, this is nozzle number 2, then this is nozzle number 3, and this is nozzle number 4. So the number of nozzles depends upon the size of the rotor, what is the incoming velocity of the steam, and what amount of energy you want to generate. That is the kinetic energy, what amount of you want to generate. So depending upon that, we are deciding the number of nozzles also. If you observe the other side of the picture, that is the right side, you can see that here we have drawn a graphical part. This is the graphical part, and if you observe here in this chart especially, you can see here the first part. This is nothing but representing the sketch of a nozzle, and you can see here when the steam passes through this nozzle, when the steam is passing through the nozzle, You can see that the cross section of the nozzle is designed in such a fashion that as it comes to this exit point, what happens? The kinetic energy of the steam, it increases. So with increase in kinetic energy, when the steam, it is striking these curved blades, what happens? Here an impulse force is generated at this end, which causes the blades to move in the upward direction, that is rotate in the upward direction. So after striking with the greater force, it moves away from these blades in this fashion. It moves away. So therefore, here at the bottom, we have drawn some of the graphs. So if you observe here, especially this point, that is point number P naught, it is a thing, but with respect to nozzle, that is from here to here, students, from here to here, whatever the graph is there, it is with respect to nozzle itself. So what he says here is, when the steam is passing through the nozzle, there is an increase in kinetic energy. At the same time, there is an enthalpy drop, that is the pressure drop is happening as the steam passes through the nozzle. You can see here, up till it reaches the part of the moving blades. Once the steam passes over the moving blades, you can see here almost there is no pressure drop, which means from the inlet of the blades to the outlet of the blades, the pressure of the steam almost remains constant. But the same, if you compare with the velocity diagram, for the velocity diagram, here you can see here, I have marked here green labeling. This is the part where the steam is passing through the nozzle. Okay, so the cross section of the nozzle already I have shown you how it is defined. It is defined in such a, this is the nozzle part. It is defined in such a fashion that as the steam passes through the nozzle, velocity increases. So you can see here in the graph, the green colored line I am showing here, from V naught, the velocity goes on increasing until it comes out of the nozzle, that is at point V1. So if you observe here, there is this much is the increase in velocity. This is the final velocity. This is the increase. This is the initial velocity. So this much amount of velocity is increased, which means there is an increase in the kinetic energy. So with this energy, when it strikes the blades, it gives away some force. That is an impulse force to the blades. So as a result, when the steam is coming out of the blades, you can see here its velocity goes on decreasing when compared to the inlet point, that is at a point V1. So in the examination, when the question is asked to write the description of the impulse steam turbine, you need to draw these graphs. So the red colored lines which you are seeing, it is nothing but it is the pressure diagram. So the red colored lines, it is pressure diagram. It is pressure diagram. Similarly, the green colored lines, it is nothing but the representation of velocity diagram. So always remember, in the steam turbines, especially for the impulse kind, the expansion of the steam, that is the pressure drop, it happens only in the nozzle. That is the red colored line you can see from P0 to P1. At the same time, as I said, always the pressure drop happens in the nozzle from P0 to P1. This is the red colored line which I am highlighting here. And as the steam passes over to the moving blades, the pressure remains constant. Also, the velocity, if you compare the velocity in the nozzle, it goes on increasing from V0 to V1. And once it passes over the blades, strikes over the blades, the drop in the velocity from V1 to V2. So this is nothing but the increase in the kinetic energy, and this is the working phenomenon of the impulse steam turbine. So those points they have highlighted here. So impulse steam turbine is a thing, but it is consisting of one or more set of steam nozzles. As I said, it may have one or more set of steam nozzles, and there will be a row of curved blades through which the steam is being passed, mounted on a rotor. Then the steam from the valve, when it passes through a nozzle, the purpose of using the nozzle is to what? As I said, it is essentially used to increase the velocity of the incoming steam from the boiler. So nozzles work is to increase the velocity of the steam. Then when this high velocity steam, when it is made to strike or when it is made to impinge on the row of moving blades, then what happens? The necessary force is developed. That force is nothing but it is the impulse force which causes the blades to rotate. Therefore, the expansion of high pressure steam, it occurs completely in the nozzle itself, especially for the impulse turbine. Please do remember this one. The expansion of the pressure, that is the pressure drop, occurs only in the nozzle itself. And then when it passes over the blades, the pressure remains constant until it comes out of the moving blades. So here I said, as the steam flows over the row of moving blades, the pressure remains the same itself. It is constant. This is for the impulse steam turbine. Similarly, we have the reaction turbine. In the reaction steam turbine, we are having more number of moving blades and the fixed blades. Here we don't have nozzles, but if you observe in the picture here carefully, the terms which you are seeing here, FB, they are nothing but the fixed blades. And the terms which you are seeing, the MB, they are nothing but the moving blades. So here we don't have nozzles, but instead of that, the fixed blades, they work in the form of nozzles itself. How it happens? Please observe here. Initially, when the steam passes through the fixed blades, you can see here, it enters the fixed blades, it passes here, changes the direction in the moving blades, again it enters the fixed blades, again it changes direction, passes through the moving blades, change in direction, fixed blades, change in direction, moving blades. So what happens throughout these blades, there's a change in direction as it passes through alternate set of moving blades, fixed blades, or moving blades, fixed blades, moving blades. So the space which you are observing here, please do observe here, whatever the space is being present, this particular space between the fixed blades and moving blades, the space itself, it is nothing but it is providing the nozzle effect. So therefore, here what happens when the steam passes through one set of the blades, then there is a reaction force being developed. That reaction force makes the blades to rotate, and it is also responsible for the steam to move for the next set of blades. So always in the reaction steam turbine, we are having the fixed blades and moving blades, a set of fixed blades and moving blades. And if you observe here in the reaction steam turbine, the pressure drop here, if you observe, especially the pressure drop in the pressure diagram, please observe here from P0 to P1 here, it is entering now which type of blades? It is entering the fixed blades. So in the fixed blades, the steam goes on, the pressure goes on decreasing. Okay. Now from fixed to moving blades, there is some gap, it remains the constant. Again from the moving blades, again what happens? There is a pressure drop. Again there is a constant pressure line, and again in the moving blades, the pressure goes on decreasing. Similarly, what happens and what we have the conclusion here? We can have the conclusion that the pressure drop in the reaction turbine, it is happening continuously, gradually for every set of fixed and moving blades. So this is my exit pressure PE. This is my inlet pressure, that is P0 equal to P1. This is the pressure diagram. This is what? It is the pressure diagram. You need to draw this correctly even in the examination also, then only the full marks will be awarded to you. Similarly, if I draw the velocity diagram, this is V0 up till here, this is the inlet velocity. Then as it passes through the fixed blades, you can see here, how is the direction of the steam? Here the direction of the blades, how the blades have been mounted. Please observe here. The blades which are observing here, they are for the fixed blades, they are oriented in this position, whereas for the moving blades they are in this direction. So their shape and orientation, if you observe, they are completely opposite for the fixed moving blades. So as a result, when the steam passes first to the fixed blades, it moves away upwards with the increase in velocity, and again it passes through the moving blades, decreasing the velocity with the reaction force developed, and it passes again to the next set of fixed blades, moving blades, fixed blades, moving blades, and this process goes on continuing. So therefore, what I can say here is the velocity initially in the fixed blades, it goes on increasing. The velocity in the fixed blades, it goes on increasing as steam passes through the fixed blades. Then once the steam passes through the moving blades, the velocity goes on decreasing. Again, it enters the next fixed set of fixed blade. Again, its velocity increases. Here it is constant. Again, when it passes through the moving blades, its velocity decreases. Constant. Again, the velocity increases in the fixed blades. Constant. And finally, to the last set of blades. Keep in mind, students, always the exit velocity, if you observe here, the exit velocity and the inlet velocity, they should be having difference. If both are same, then you cannot say that the energy is being generated. That is, there is an increase in kinetic energy. So you should have this particular point in your mind. Now, as I said, the reaction turbines have alternate rows of fixed and moving blades, where they are mounted on a rotor. These moving curved blades, they are shaped similar to the fixed blades, but the thing is, they are fixed in what? The reverse direction. That is the reason that you can develop the reactional force and the velocity can be transferred. If you are mounting in the same directions, then you cannot have the reaction force developed and the effect of the nozzle also. Then the moving blades, when they rotate, they are having an impulse type of steam as well as expansion, due to which the acceleration of steam is related to the blades. This expansion of a high pressure steam occurs in the blades mounted in the fixed row as well as for the moving row. As I told, the pressure drop occurs in the fixed blades as well as in the moving blades also. These are some of the points which you need to remember for the reaction turbines. Now, comparison, as I said, we are having some of the comparisons in terms of impulse turbine, reaction turbine, and we are having the factors also. The first factor is regarding the steam expansion. As I said, for the impulse turbine, the expansion takes place only in the nozzle and that too towards the condenser pressure. Whereas in the reaction turbine, here expansion happens partially in the nozzle, brought to the condenser, and then it expands even the subsequent blades also, that is both the fixed blades as well as the moving blades. Then if I come for the relative velocity, this remains unchanged as there is no friction which can be considered for the impulse turbine. Whereas when I compare for the reaction turbines, there is a friction force developed due to which the relative velocity at the exit is always greater than the inlet. Then coming on to the blade profile, that is the blade design. So I have seen in the impulse turbine, we are using these kind of blades throughout the rotor. So if you cut these blades into equal parts at the center, what happens? They are symmetrical in nature. Whereas in the reaction turbines, the blades are mounted like this. They are aerophilic structure in nature. They are aerofoil structure in nature. They are unsymmetrical. They are unsymmetrical. Similarly, the steam velocity at inlet, especially for the impulse turbine, it is very high. Whereas for the reaction turbines, it may be moderate or even less also. Then the blade efficiency or stay efficiency, especially for the impulse turbines, it is very lower, whereas for the reaction turbines, it is higher in nature. Number of stages per enthalpy drop here in the impulse turbine, it takes place within a few stages, whereas for the reaction turbine, it happens more number of stages because we are having alternate set of fixed and moving blades. Okay, so this is some of the comparisons of the impulse turbine as well as the reaction turbine. So with the comparison of the impulse and reaction steam turbines, this is a theoretical point regarding the steam turbines. So in today's session, we'll be stopping here itself. In the next session, we'll be starting with the analysis of an impulse steam turbine for a single stage, where we're deriving or derivation known as condition for maximum blade efficiency. And we'll be discussing some of the problems on the steam turbines, that is the impulse case, using the graphical method. So we shall stop here, students.